Hello class, today we're going to go over 11.8, which is the power series. Now we're really getting into the nitty-gritty of this chapter. So first thing I want to talk about is the power series, and all the power series is really what it's doing is it's something that's a coefficient times a variable to some exponent. And so when we write this in an expanded form, we're going to get C naught, whatever that constant is, plus our C1 with x to the first power, then C sub 2 to x to the second, C sub 3 to the third, or x to the third, and then so forth and so on. So what's going on here is it's called the power rule because our exponents are being impacted. So you can see the exponents are growing. Now, this one here is centered at 0. Much like when we had vertices and things like that, the x minus a piece, right? The a was the center, or our shift. In this case, in the general case, when we have something like this, what's going on now is this is going to be centered at a. And so just like we had with parabolas and different functions like that, the x minus a, that a shift is going to be in this case to the right. If it would have been x plus a, it would have been some sort of shift to the left, kind of just to make a connection to what you'd already know. Okay, so let's go ahead and use this and see if we can make some connections to some of the information that I've already provided in my other lectures for you. So here's an example, and it says that for what values of x is this series convergent? And so what we need to do is be able to look at this. We don't know much about this one, so what we're going to do is we're going to see if we can do a ratio test and see if the ratio test can help us with this. So in this case, by the ratio test, I'll write that down so you know it. By the ratio test, then I'm going to say a sub n is equal to n factorial x to the n. And we're going to use it for when x isn't 0. Because if x was 0, this thing would obviously be convergent at 0. So let's look at it. So by the ratio test tells us to take the limit as n goes to infinity of a sub n plus 1 over a sub n. And we're doing it absolutely. So the limit as n goes to infinity of this thing is going to be n plus 1 factorial to the x to the n plus 1. That's going to be my a sub n plus 1 over my a sub n, and we have that as n factorial x to the n, correct? So what we can see from here is I can rewrite it to where it's n plus 1 times n factorial, so the n factorials cancel out. And I can also get rid of all of the x's except for 1. So what's going to end up happening is I'm going to have the limit as n goes to infinity of n plus 1 and then absolute value of x. Well, if n is going to infinity, I'm going to have infinity plus 1 times my x, and so that clearly tells us that this is going to take off to infinity. And so we know by the ratio test that this series will then diverge, right? So by the ratio test, by the information that I gave you in the last section, this series diverges when x is not 0. And again, just to recall, this does converge, and it only converges when x is equal to 0. So that's important for you to remember. This series converges when x is equal to 0. Because if we build it, we're going to see that it's always going to be that x being 0, right? Makes it very uninteresting. So we want to do the interesting cases, not the uninteresting. All right, let's do another example and see what we can get. All right, so in this example, we're going to let a sub n equal x minus 3 to the n over n. And then again, we'll do this by the ratio test. And so remember, the ratio test is a sub n plus 1 over a sub n. And so we'll get x minus 3 to the n plus 1 over n plus 1. But now instead of dividing by that fraction, I'm just going to multiply by the reciprocal of a sub n. So I'm going to get n over x minus 3 to the n. And we can see from here that this is going to clearly simplify. So I'm going to get 1 over n plus 1 times x minus 3, and this should be an absolute value. But that can be cleaned up a little bit to be 1 over 1 plus 1 over n times the absolute value of x minus 3, which as n goes to infinity, we see it's just going to be x minus 3, right? And just so you know, that's as n goes to infinity. That's us taking the limit of this piece, right? So I could have written, all right, here, shoot, that's not going to work. If I'd have done it, if I'd have wrote here the limit as n goes to infinity, you would see what I'm talking about. You could see that that's going to become 1 over 1 times the x minus 3, which will be x minus 3. And so now from here, we know that by the ratio test, the given series is absolutely convergent. And then we remember, if something is absolutely convergent, then the series is going to be convergent, right? And therefore, convergent when absolute value of x minus 3 is less than 1, right? Well, that was part of the ratio test. And divergent when x minus 3 is greater than 1. So what this implies is that we're going to be convergent from between 2 and 4, and then divergent when x is less than 2 or x is greater than 4. And I can show you that. All I'm really doing here is this is the convergent piece, right? And so if that's the convergent piece, that's where I'm going to get my 2 and my 4. And then the divergent piece, I didn't write that down, and divergent here when we have this. So what's going to happen is this one solved is going to give me this. This one solved is going to give me this. Now, the one thing that it didn't address that we need to address, and the ratio test doesn't help us with this, is at 2 and at 4. So I have to address that independently. So I'll do it below this theorem, and then I'll come back to this theorem. So the ratio test, the ratio test tells us nothing when x minus 3 is equal to 1. So that means we need to consider x equals 2 and x equals 4. So let's do it. So if x equals 4, the series becomes the sum of 1 over n, which is divergent, right? And the reason we know that's divergent is p series, right? So that's something that you need to recall. And then if x equals 2, the series becomes the sum of -1 to the n over n, which converges, and that's by the alternating series test. And so our convergence, therefore the convergence interval, is including 2 but excluding 4. This is the convergence interval. Okay? We can talk about this in more detail as we do examples in class, but we're going to have to be addressing the endpoints now more and more as we go. Okay? So now going to this theorem tells us that if we're given a power series, right, where it's centered at A, there are only 3 possibilities, right? It converges only at A. That was that case that we did with the x equals 0. The series converges for all of the x's, or we fall into this situation where we have it's convergent for less than but divergent for greater than. That was what ended up happening here in this theorem, and I wanted to lead to that by showing this here. But these are the 3 possibilities that happen with this theorem and that I used in this example. Now, one of the other things that you'll want to know is some examples of series that have convergence and their intervals of convergence. So remember, the one that we did here, the only time that it was convergent was when x was equal to 0, and so we see that only at 0 is it convergent, and its radius of convergence is 0. The geometric series has a radius of 1 because you remember that the absolute value of x has to be less than 1 in order for the geometric series to be convergent. And then here are some other examples of radius of convergence and intervals of convergence. So let me do another example for you that's going to involve some work that's going to demonstrate finding the convergence, the radius of convergence, and the interval of convergence, and how we attack it. So here we go. So in this example here, what's going to happen is, again, I'm going to try to attack this with the ratio. So I'm going to go a sub n plus 1 over a sub n, and that's going to give me -3 to the n plus 1 x to the n plus 1 over the root of the quantity n plus 2, and then I'm going to multiply that by the reciprocal of the fraction, so that's going to be n plus 1 over a -3 to the n x to the n. And then we see that this is just some algebraic manipulation, so you should be able to see that we're going to get -3 times x, and we're going to end up with the root of n plus 1 over n plus 2, and this should be an absolute value. So what this tells me is I'm going to get a +3, and then on the inside I'm going to manipulate it a little bit by dividing everything by n. So I'm going to get 1 plus 1 over n over 1 plus 2 over n. Absolute value of x, right? Because that's where the restriction comes into play. And we know that as n goes to infinity, right? What's going to happen here is this implies that this is going to be 3 times the absolute value of x. And we know that again as we take the limit of this going to infinity, right? So this is as n takes off to infinity. And so by the ratio test, we know a couple of things, right? The ratio test tells us that 3 times absolute value of x, if it's less than 1, is going to be convergent. Or it converges, if you'd like. And then 3 absolute value of x, if it's greater than 1, is going to diverge. which is perfectly cool. We now know that. We can find those values, and those values are pretty easy to find. So we know really absolute value of x less than 1/3 and absolute value of x greater than 1/3. So we see that where we have concerns in terms of the endpoints are going to be at 1/3 and a negative 1/3. So we know that the convergence is going to be between 1/3 and negative 1/3, right? That's just algebra from looking at this. But now we need to see if either one of the endpoints is included as part of the convergence. So let's try to do that. So let's consider the x is equal to a negative 1/3 first. So what ends up happening there is I'm going to get my summation 0 of negative 3 to the n, negative 1/3 n over the root of n plus 1. And so that's going to give me the sum of n equals 0 of 1 over root of n plus 1. So you can see I'm doing a comparison to something that we already know. And this is 1 over root of 1 plus 1 over root of 2 plus 1 over root of 3 plus 1 over root of 4. And we know that this is going to continue, and this implies it's going to diverge. So it diverges at negative 3, right? Which is pretty sweet that we were able to figure that out. Now let's do for if x is 1/3. And what's going to happen here is we're going to again have that same value. And what that's going to give me is summation n equals 0 of negative 3 to the n of 1/3 n over root of n plus 1. And what's going to happen here is this is going to be equivalent to this. And we know this one because of the 1/3 being able to not be a concern. We end up seeing that this one is convergent. And the reason it's convergent is by the alternating series test. And so we know 1/3 is included. So remember the convergence interval. Occurs at negative 1/3 to 1/3, but 1/3 is included. So there we have it. So the radius of convergence we see is what in this case? It's important for us to be able to notice what the radius of convergence is in this case. The radius of convergence is 1/3, and this is the interval. So 1/3 is the radius, and negative 1/3 to 1/3 included is the radius of convergence for this problem. Okay, let's do another example, and then we'll call it a day for 11.8. Okay, so looking at this here, it says find the radius of convergence and the interval of convergence of this series. So again, we're going to be looking for two things. We're going to be looking for the radius, and then we're going to be looking for the span that it's going to be convergent on. And so again, to do this, you got it. It's going to be a ratio. And so we're going to get n plus 1 x plus 2 to the n plus 1 over 3 to the n plus 2 times, and then the reciprocal of what our original was, correct? So x plus 2 to the n in absolute values. And then we see things will cancel, right? Which is always so nice. We'll get a 3 in the denominator. We'll have an x plus 2 left, and then we should have n plus 1 over n in fact, yeah, times absolute value of x plus 2 over 3. But this can be cleaned up a little bit. Right, and again, if we take the limit of this, we see it's just going to be 1, right? So as we take the limit of that, we should get 1/3 absolute value of x plus 2. And this is as n goes to infinity again. So we can see something cool. Again, by the ratio test, we know that absolute value of x plus 2 over 3, if it's less than 1, converges. And x plus 2 an absolute value over 3, if it's greater than 1, it's going to diverge. And so that tells me that x plus 2 less than 3, right, in absolute value, and x plus 2 greater than 3 would diverge. So now we know what the radius of convergence is for this. We see that the radius of convergence is that 3. And this time I'll actually write it down for you. So the radius of convergence is r equal to 3. So on the previous one it was r equals 1/3. So now we know that it's going to be from, it looks like -1 to 5. Now we need to determine if -5 or 1 are included in the interval. So we have to test the endpoints, right? So here we go. So if x is equal to a -5, I'm going to have this sum n equals 0 of n times -3 to the n over 3n plus 1. And this we can pull out the 1/3, so we have something that we can clearly see, which is going to be -1 to the n times n, right? Because the n factor there is just going to continue to just be able to be pulled out, and that's by in 11.2 we were able to demonstrate that with the test for divergence. And so we know that this is going to diverge by that test. And again, like I said, this is from chapter 11, section 2. So it's something that you should have a reference to. And again, it's that -1 to the n does not converge to 0. Right? It doesn't converge. The oscillation doesn't converge to 0. So the gap isn't getting smaller and smaller and smaller. It's staying essentially the same or growing. Now let's check at 1. And so again, oops. So we're going to get 1/3 the sum of n equals 0 of n. That's how that one cleans up. And again, by the divergence test, this is going to diverge by the test of divergence. And so our answer for this one is the interval of convergence is from -5 to 1, both excluded. So we found the radius is 3, and this is the interval of convergence for this. This is 11.8. It's not too bad. 11.9 and 11.10 will just become more and more practical, which will make life so much more fun for us all. All right, all the best. I'll see you guys soon.